Hey there, college algebra folks, back here with a few more videos for you that are going to illustrate examples of the material we're going to use to kind of wrap up our semester. And what we are going to be looking at in this last chapter is focusing some attention on what we call systems of linear equations, right? Here we have a system of equations given here, right? Focusing in on this system of linear equations and solving these, right? Looking for solutions, right? And incorporating into that process some work with matrices, right? Or a matrix value. And what is a matrix? A matrix is nothing more than a list or a grouping of values that are arranged into some sort of set, right? Where what we're going to arrange our matrices or these sets of values into are going to be these what we call linear matrices or linear matrices, right? We're going to make a linear matrix out of the information that we see presented in these systems of linear equations, and then use some what we know as linear algebraic process, right? This is really the beginnings of some linear algebra study to go about finding and working with the solutions to these equations, right? Which we're going to see is really going to be a methodology that is going to simplify some things that we really already understand how to do in the algebra. And it's going to be a methodology that is really at work in the background as we solve some of these equations with what we currently understand as techniques, which are some of the techniques I'm going to illustrate here in section 6.1, right? But what we're developing is this process that will be able to be extended, where you be able to take these ideas out and look at this for more complex systems of linear equations, all right, or just more complex systems of equations in general. So that is what we're setting ourselves up for here at the end of the semester. These ideas do happen rather quickly. We don't go terribly complex in our systems. We try to keep them to two equations with two variables, right? Overall, there won't be much complexity over that in a lot of our work, right? And these ideas kind of stepping forward at the same time stepping back a little bit. We are going to be back looking at linear equations, but we are going to be looking at them in the context of systems, and we are going to be bringing in this idea of matrices into the matrix, the linear algebra, into our study here. All right. Now, to begin with, in this first question here, it does ask, is this coordinate 5, -1 a solution to this system of equations? All right. Now, we know what it means to be a solution to just any given equation. To be a solution to any given equation means when you substitute it in for the values of the variables, it makes that equation true. For instance, if I take this first equation here, 3x minus 3y equal to 18, and I let xy be equal to the value 5 comma -1, right? That does mean I just substitute in for the value of x, the value of 5, and I substitute in for the value of y, the value -1, and I ask myself, is that statement true? If the answer is yes, it's a solution to that equation. If the answer is no, or false, right? That coordinate is not a solution to that equation. And what we had noted is that this equation actually has probably an infinite number of solutions. And if it has an infinite number of solutions, we can put all those solutions side by side on some xy coordinate plane and actually form the graph of this equation, which would be an illustration of the graph of its solutions, right? Really what we're looking for here is this one coordinate. Is this one coordinate on the graph of this equation? Well, we can do the math here. Shouldn't be too long to answer this. It is linear equations we're working with here. 3 times 5 is 15. -3 times -1 is +3. And does that equal 18? Well, it absolutely does, right? That is true, right? So that is a solution to this first equation. Now, to be a solution to a system of equations, this coordinate has to make every single equation in the system true at the exact same time, or what we sometimes say is simultaneously, right? What we have to come back and ask is this answer true? Is this question true for the other equation in our system, right? So we might note 2x plus y equals 9 is our equation, and we're going to let xy be again equal to this coordinate 5, -1, right? And we're going to ask, is that true? Are we going to make a true equation here when I go 2 times 5 plus -1? Does that equal 9? Right? And it shouldn't take long to see, yeah, 2 times 5 is 10, plus a -1 is just -1. Does that equal 9? Well, it absolutely does again, right? Check. It is true, right? Since 5, -1 makes both of these equations true, what we say simultaneously at the exact same moment, right, in the system, then this location, 5, -1, is it a solution to the system? The answer there is yes, right? Yes, 5, -1 is a solution, right? As it makes both equations true simultaneously. Right? Now, one other thing I will point out here, folks, is again, we go back to the idea that this is a solution on this equation. This is a solution also on this equation. And what I mean by that is they are points on the, this is a point on the graph of the first equation, and this is a point on the graph of the second equation. And these two equations are certainly different from one another. But if we were to look at their graphs in that two-dimensional space would intersect each other at this location, highlighting that solution behavior. And we should be able to see that if we look at the graphs, right? Let's consider perhaps just rewriting these, right? To actually put the graphs into our calculator here. Let me just change my mode back. In fact, what I probably ought to do is just erase the entire calculator memory. All RAM, reset, right? Let's take the equation 3x minus 3y and let's get it into a form that we can put into our calculator. Now, keep in mind that put an equation into our calculator, I'm going to put that underneath my y equals menu where I need to solve this equation for y. So how do I solve it for y? Well, I might add 3y to both sides. Or not 3y, 3x. You could add 3y, but let's add 3. And then we wouldn't be adding, we'd be subtracting. Let's just approach it this way. Let's subtract 3x from both sides, and then let's divide both sides by -3. Now, when you divide on the right by -3, you are going to have to divide everything by -3. Every term gets divided by -3. So that does leave us with y equals 18 divided by -3 is -6. -3 divided by -3 is plus 1x, or you might say this is y equals x minus 6. So that's our first equation, x minus 6. We're going to put that in our calculator. It has its respective graph, right? And then let's take our second equation, 2x plus y equals 9. Solving that for y is pretty quick. You just subtract 2x from both sides and you get 9 minus 2x. So if we go back now and we put 9 minus 2x into our calculator and we graph that equation, we end up with this graph here put into place. And what we're interested in is this location right here where the two graphs happen to intersect. Now, if you look at my Windows settings, I did reset my calculator. So I do have some rather standard Windows settings on this graph. This goes from -10 to 10 for x, -10 to 10 for y. And what we're looking at is this location right here, 5, -1, 1, 2, 3, 4, 5, and down 1, it is that location right there on my graph. All right? So we can see right there in my graph, I see that location at 5, -1. Now, what there is on our calculator that is interesting that we can do to help us solve these systems at times is there is a way of actually giving your calculator find that point of intersection. If you notice, you have your calc menu here, right? You could do second trace and it will open up your calc menu, and the 5th option down says intersect, and your calculator will calculate the intersection of two curves. So I could show you that real quick here, right? If I just hit enter, it did bring up the graph again, and it's asking you a question down here. It's asking you, what is the first curve that you want to look at finding the intersection with some other curve? And it's saying that right now I'm on the curve y = x - 6. I'm on the first graph you made. And actually you can see right there, you can see that cursor flashing. And I can actually move it left and right along that curve to make it a little bit clearer that that is what it is highlighting right now as our first curve. Now, if that is not my first curve, I can use the up and down arrow key to actually jump from graph to graph. And you can see I've moved over here now to graph y2 instead of y1. And it's asking, is this now your first curve? Now, if that's not my first curve, I can continue to use my arrow keys up and down to jump from graph to graph to look at the graphs that I'm interested in finding the intersection of. So, yeah, maybe I jump up to the second graph and say, yeah, that's my first curve. And then it asks you for your second curve. Well, I'll say, okay, then the only other curve I have in here is this other one, x - 6. So, yeah, that's my second curve. And then it wants you to make a guess, because at times graphs intersect more than once, right? Or you might have more than one intersection point that the calculator sees. So you want it to go to the one that you're observing. And right now we're observing the one here at 5, -1. So I'm going to come up here with my left and right cursors and move along until I get pretty close to 5, -1 for my x and y values. I get that location pretty close. Now, now this is if you have more than one. In most linears, you're going to have just one, so you can get away with just hitting enter. You don't have to be terribly close. And what you'll notice is it'll jump right to that location as a cursor, and it will spit out and tell you what is the intersection you're looking at. And that is the intersection 5, -1. Yeah, it checks our answer here, right? It says, yes, I am a solution. Calculator methods, folks. You want to use your calculator if you're struggling with some of these ideas to begin with. All right? Now, if we go a little further, there are a couple of techniques we have for determining the solution to a set of linear equations. And I will tell you, this section is a bit of review, folks. Right? These ideas really are, I hope, nothing new to you. What's going to be new is the matrix work, is working within the matrices to solve these systems. And I will be honest with you, by the end of this few videos, we're going to know how to solve these systems on our calculator. Besides just looking for this point of intersection, how we're actually going to be able to use some other matrix commands on our calculator to actually begin solving this. So it's nothing more than just a few button clicks, right, to find our solution. All right, we can get away with doing very little algebra at all. All right, cool. So here's our next equation. Determine the solution to the following system here. And it does give us a specific method. We should be familiar with substitution method. In substitution method, you're going to pick one of the equations. You're going to solve for one of the variables in one of these equations, and then take that value of the variable and substitute it in to the respective variable in the other equation. And what that will form is a one variable equation that you can then solve for that one variable. And with that one variable found, you can then find the initial variable involved in your substitution using one of the other equations, or two variable equations. So here We have 4x plus y equals negative 6, and we have 5x plus 9y equals negative 13. Now, out of these two equations, the one that we might solve for its variable might be this first equation. And because it's happening all by itself with no other constant multiple out in front of that value of y, we might consider solving for just that value of y. The algebra involved would be minimal to solve for the value of y in this equation. All I would have to do is add 4x to both sides. So I end up with y equals 4x minus 6 if I arrange that with the x term first. Right? Now that's a pretty quick solution there. So that sets us up convenient for substitution, where now I'm going to have to go into this other equation, and at that value of y, I'm going to have to substitute in, right, this value of y seen here. So for 5x plus 9y equals negative 13, right, we can say that 5x plus 9 times 4x minus 6 must be equal to negative 13. And what we now have here is this linear equation in one variable that we should be familiar with solving, right? We are going to have to distribute the 9. Folks, the end of the semester, you should not be forgetting to distribute when appropriate. This is 5x plus 36x minus 54 equals negative 13, right? Where I now combine these like terms and get 41x minus 54 equals negative 13. And I then, what? Add 54 to both sides. Get 41x equals 54 minus 13 is actually 41. So when I divide out the 41, this one conveniently yields the value of x equal to 1. So x in my solution set here is the value of 1, where I can now go back to any one of these two variable equations I have presented here, substitute in this value of x, and it will tell me what my value of y is. And actually, this is probably the equation that might be most convenient. As you can see here, we've expressed y as being dependent upon x, right? Where, right, we might say here, implying for y equals 4x minus 6, y is equal to be 4 times 1 minus 6. Well, 4 times 1 is 4. Minus 6 ends up yielding negative 2, right? Thus, we want to make sure we get that coordinate expressed correctly. It is an xy coordinate. Changing the order here, folks, will be an incorrect answer, right? Thus, the xy coordinate that makes this equation true is this value of x and this value of y, right? X equal to 1, y equal to negative 2 in value. All right? That's solving using substitution method. We all should be familiar with that method. All right? Ooh. Let's look at the next case. The next case here. Asks for you to solve the system of equations using what we call elimination method. Right. Here we have a system of equations, and we're asked to solve it using what we call elimination method. Now, this is different than substitution. What elimination method does is it works with both equations at the same time to begin with. Where if I express these a little bit clearer here, right, this works with both equations at the exact same time to begin with here. Right? It starts off here trying to eliminate one of these variables by doing what we call vertical addition through that equation. What we can note is we can actually add vertically through these equations and build a comparable relationship in our system of equations, right? That doesn't always produce convenient results, right? If we attempt that here in this case, this does produce just another two-variable equation that is what we say comparable to the relationship seen between x and y here in this equation, right? But it doesn't really eliminate any of the variables when we do that, right? But along with being able to add any row to another row, right, in this elimination method, what we're also able to do is take and multiply any row by a constant multiple and replace that row with a constant multiple of that row. Not only could I dump this into any one of these rows and replace a row with this quantity here, I could multiply either of these equations by a constant multiple and replace the entire row with that result. What I might consider doing here actually is coming along and in this first row, I might consider just multiplying that entire row by the value with 3 and replacing it with its result over here. And if I did that, I would just get 12x plus 15y equals, now 29 times 3 is what, 87 in value, right? 3 times 20 is 60, 3 times 9 is 27, so that does give us 87 in value. And then what I might consider doing here down to this bottom row is multiplying through the row by, let's go with positive 5 in value. Now, where I'm getting 3 and 5 from might become a little bit more obvious when I look at what happens over here in this result. As that 5 distributes throughout that row, that does become 10x minus 15y equals, now 5 times 13 is 65, but it is negative 65. Where with that result in place, if I now add vertically, I do get 12x plus 10x is 22x, but in the second column here, positive 15y minus 15y added together zeros away. And the variable is what we say is eliminated. So this is where we get the name for this method called elimination method. Now if we add 87 to 65, that does result in what? You should be able to see that. That is going to be 22 in value. Where you have really just 22x equals 22, implying x equals 1 in value if you divide both sides by 22. Right? With that x equal to 1 in place, right, we can now go back to any one of these two variable equations in our relationship, substitute in that value of 1 for x, and solve for our value of y. Right? I can even go into this one here if I would like. Right? And we can note if I plug in 1 there, that would be 6 times 1 plus 2 times y equals 16. So that is 6 plus 2y equals 16. Or if I subtract 6 from both sides, this is 2y equals 10. Or if I divide by 2, this is now y equals 5 in value. Right? So x comma y equal to 1 comma 5 is the solution. It makes both of these equations true simultaneously. And we should be able to check that. If I take 1 and plug it in here, 4 times 1 is 4, plus 5 times 5 is 25. 4 plus 25 is 29. And if I plug in 1, 5 here, it should equal negative 13 in value, right? 2 times 1 is 2, minus 3 times 5 is negative 15. 2 minus 15 is negative 13 in value. And you notice I substituted x into this equation, which wasn't even given by the system. Right? It was the sum of the two rows in the system, and it still worked for me in finding that solution, folks. I didn't work with these two rows. I multiplied both these rows by some number and replaced those rows with those values, and it still worked in the process, folks. Right? This is the solution to this system. All right. All right, folks. Apparently I ran out of time on that last video. They will only record for about 30 minutes before it shuts off, so I got to really watch my time on these. But I got cut off here in the middle of this fourth problem, so I'm going to come back over this and clarify all this in this section of the video here. Again, what we see going on in this word problem is we do see a system of linear equations being presented in what we might say is the real world context here, right? It says here, a vendor at a local fair sells hot dogs and hamburgers for the cost of supplies. The vendor pays 50 cents per hot dog and $1.25 per hamburger. If the vendor spends $500 on supplies for hot dogs and hamburgers and sells out all 550 items, hot dogs and hamburgers, how many hot dogs were sold? Right? How many hot dogs did the vendor buy and sell if these are the conditions on the system? Right? Now, if this is a system of equations and these are the conditions on the system, that means that there are a couple of unknowns in the problem, and there are a couple of equations we can prepare with those unknowns. And if we think about the problem, there are really two unknowns. What we aren't told about in the problem is what we might call x, that being the number of hot dogs sold, bought and sold, right? And we're not told about y being the number of hamburgers bought and sold. We know a little bit about how they relate to each other, right? We know we sold 550 hot dogs and hamburgers, right? So we know x plus y equals 550, right? And we know how they relate to each other in terms of how much we spent on them all together, right? If we take 50 cents times the number of hot dogs we have bought and sold, and add that to $1.25 times the number of hamburgers we have bought and sold, we know that that should add up to that $500 in total. Here is the system of equations represented by this problem. All right, and we can solve it using one of two means. We can either solve it using a substitution method, or we can solve it using elimination method. Here we might say it sets itself up kind of nice for a little bit of elimination method. I can solve for either one of these variables pretty quickly. Let's maybe take this and solve for y. Right? To solve for y, I just have to subtract x from both sides, right? Y would just be equal to 550 minus x. Where I'm able to take now that value of y, 550 minus x, and substitute it back into the second equation for this value of y. All right? This entire 550 minus x can now be substituted back into that entire equation. And let me go ahead and change these over to fractions. This might work a little nicer for us. 1/2 x, 50 cents is 1/2 x, plus $1.25 is 5/4 y. Now, y is being replaced with 550 minus x. So let's replace that with 550 minus x. And then what do we know all that equals? That all equals 500 in value. So there is our equation. I went ahead and expressed the decimals as fractions because I do like to work within the fractional system. Because I can do the algebra most times by hand, right? A lot easier than working with the decimals. I can now eliminate the fractions, and I could have eliminated the decimals up here. It's just the scale of my numbers would have gotten really large rather quickly. Whereas I can eliminate my fractions down here using a similar idea of just multiplying through that equation by some common denominator. Now, what is my common denominator of 2, 4, and 1? Well, the lowest common denominator would be 4. All right? So 4 times 1/2 is 2x. 4 times 5/4 is just 5. The 4's cancel in that case. And 4 times 500, that would be 5 times 550 minus x. And then over here you'd have 4 times 500 would be 2,000 in value. Now if we distribute the 5, we will get 2x plus, now 5 times 550, 5 times 500 is 2,500. 5 times 50 is 250, so 2,500 plus 250 is 2,750. Minus 5x must equal 2,000. Right? Combine your like terms, 2,750 minus 3x must equal 2,000. And there's our nice one variable linear equation that we solve for. Subtract 2,750 from both sides. You will get negative 3x equals negative 750. And lastly, divide both sides by negative 3, and you will find x equals positive 250. The negatives cancel and getting you back to a positive result here. Where what is x? Right? X is our number of hot dogs. Right? What we can say here is in this problem, the number of hot dogs sold, well, there was 250 hot dogs sold. Right? And if x plus y equals 550, plugging in that 250 here and subtracting it from both sides, you will find y. Y would be equal to 300 hamburgers. Right? There is the solution to our system. They want a number of hot dogs sold, so 250 would be the number of hot dogs sold. All right, folks. Again, this is just a bit of a review section, right? You've seen problems like this before, right? What we're going to be doing is adding that matrix context to this in the next few sections. All right. If we look, there is one other part to this, one more quick word problem involved that is related to this problem. Oh, hold on, that's on another sheet. All right. We might consider the case where the vendor knows a little bit about demand with regards to his supply. Right? So if the vendor knows for every 3 hot dogs, 5 hamburgers are sold, and the vendor has a budget of $500 to buy supplies for these items, how much supplies for each should the vendor purchase? Again, we understand that it's 50 cents a hot dog, $1.25 per hamburger, right? We have those initial conditions as we had in the previous problem set up in the beginning. Our unknowns are, again, x equals number of hot dogs, y equals number of hamburgers. It's important to label your variables, folks. When you get to the end and you find x equals some value, you can quickly go back and see what x was set up to be in the problem, right? And then it also helps you in laying out your equations and keeping track of values. All right? So they budget of $500 to buy supplies. So we know where that equation might come from. It's going to be 50 cents per hot dog plus $1.25 per hamburger must equal $500 in this problem. Right? That is our first equation. That comes from the amount of money that he has to budget for supplies. Right? At 50 cents a hot dog, this would be the cost for all the hot dogs. At $1.25 per hamburger, this would be the cost for all the hamburgers bought. All right? Now, the other bit of information, the other equation in our problem is going to come from the supplier or the vendor knowing that for every 3 hot dogs sold, there are 5 hamburgers sold. What is that equation, right? This is a little tricky, but in a demand problem, if you're trying to determine these linear equations, you always want to remember is you are dealing with a linear problem. And if you can figure out 2 points on that equation, right, or on the graph of that equation, you can figure out the equation for the line. Right? What are 2 points on this equation? Well, the first point is knowing that if you sell 3 hot dogs, 3 values of X would be equivalent to 5 values of Y. What's another point might be that if you sell 6 hot dogs, you would expect to sell how many hamburgers? Well, you would expect to sell 10 hamburgers, right? And with those two observations, you have, right, 2 points that exist on the line for this relationship between X and Y, right? You can set up the slope, that's change in Y over change in X, right? 10 minus 5 over 6 minus 3 is 5/3. And then you can use your point slope formula, right? That says Y is equal to 5/3 times X minus one of these X coordinates, -3, plus the corresponding Y coordinate for that X, plus 5. And what you will see is this does simplify to Y equals 5/3 X minus 5 plus 5. When you distribute the 5/3, the 3's cancel, leaving you with just minus 5 there in the second part of the distribution. So if these 5's simplify away, then you are left with Y equals 5/3 X. That is the second equation in this relationship. Now again, this one does seem to set itself up nicely for a little bit of substitution. Things have already been solved for the value of Y. To do that elimination method, we would have to line up all of our corresponding like terms. Right? So what we might do here is let's go ahead back to fractions. This would be 1/2 X plus 5/4 times this value of Y would be 5/3 X must equal 500. Let's go ahead and distribute this out. This would be, 1/2 X plus 25/12 X would equal 500. These are like terms, right? This would be 6/12 in equivalent form. So 6/12 X plus 25/12 X would be 31/12 X would be equal to 500. So what is X? We would multiply both sides by the reciprocal of the fraction 31/12. So you could say that's 12/31, right, on both sides. This will cancel on the left, leaving you with just X, number of hot dogs sold, right, where X is going to be 500 times 12/31. Now this is where I might break out that calculator. Right, clear. 500 times, I could do times 12, that's certainly 6,000, right? Enter, divided by 31, right? We get 193.54, and we might go ahead and convert that back over to a fraction. Okay, it doesn't really simplify. It's 6,031. Right? We end up with 6,031, right, as the number of hot dogs sold. Right? Now it is asking not how much he bought, but asking how much he should buy. So if we interpret that back as its decimal value, that is about 194 items, right, for X. Now, if we want to figure out Y, we might go back into this equation here and substitute in what we know for X. That would be 5/3 times 6,000 divided by 31. I'm going to use the fraction to make this accurate. Right? We do get a little canceling here. That is 10,031, right? I don't know if that simplifies. Let's go ahead and turn that over to a fraction and just see what we get. Nope, doesn't simplify. So that as a fraction, so that is nice. That's about, what is it? 323 items, give or take one or two of the other, in order to make sure they meet their budget concerns. right? Y is the number, or sorry, X is the number of hot dogs, so about 194 hot dogs, and Y is the number of hamburgers, so that's about 323 hamburgers, right? If we notice 194 times 50 cents plus $1.25 times $323, we are 75 cents over budget. So we might have to kick off a hamburger or kick off a couple of hot dogs there. And actually, I think you'd probably kick off a hamburger, right, as opposed to kick off 2 hot dogs, right? Just to get as close as you could to that particular budget and those demand concerns, right? But folks, this is again real world problems illustrating, right, that in the context of the real world here, you are going to have a couple of variables and a couple of equations you can build with those variables and with given information in the problem. And once you have both of those equations, you can solve that system really using any technique you'd like, substitution method, elimination method, and even break out your calculator at times. And I would only suggest using your calculator, though, to check your answers. Certainly, if solving these equations, you can make a mistake, put in your calculator incorrectly. Your calculator only shows you what's in the graph window. If you may be hunting around looking for the graph, right? You still have to know the paper and pencil techniques. Calculators are a bit more of a check step, right? But with that said, that does wrap up this bit of the lecture. And this is, again, like I said, a review section, folks. What you're going to see follow here is some new material. And I do think we're going to jump up into section 6.3 next. You should be following along there. 6.2 looks at systems of, I believe, 3 variables and 3 equations. And as I said, we're going to try to keep it a little simple here at the end. Right? So I'll be back in my next video. Hope you're hanging in there. See you then.